So it is my pleasure to welcome Bob Sedgewick from Princeton University. Bob is the founding chair of the Department of Computer Science at Princeton, and it now holds the William O. Baker Chair. He is also on the board of directors of Adobe Systems, and he has been a visiting researcher at a number of different places: Xerox PARC, IDA, INRIA, which is the French National Computer Science Institute, where I first met Bob, and Bell Labs. Bob did his PhD thesis under Donald Knuth. He did he told us everything that there was to know almost about Quicksort. I guess there are a few things that were left undone. And many of you in computer science also know him for his work with Quicksort. He was co-inventor of red-black trees. And you probably also know him through his textbooks. He's written how many textbooks?
19
textbooks on algorithms, analysis of algorithms, and the definitive work with Philippe Flageolet on analytic combinatorics. Recently, Bob has been working with MOOCs and MOOC technology. He has a very popular course on Coursera on algorithms. And in fact, it was rated as one of the top 10 MOOCs on Coursera, or is it one of the top 10 MOOCs?
of all time.
Of all time, of all time. So, there you go. And he has been transferring this technology to 3 different courses that he and others have been teaching at Princeton. They did this for the algorithms course, and then they did the analytic combinatorics course, and more recently, they have done this for their introductory computer science course. And since Bob is Bob, he wrote a textbook for this course as well. And it is, I think, one of the things that we need to be looking at here at the University of Michigan, because it's pretty clear, especially for those of us in computer science, that things cannot continue as they have been, that we need to find new technological solutions to some of the problems that we're having. And Bob is going to give us some insights into this problem. He's going to talk about the 21st century model for disseminating knowledge. Bob?
Thanks very much, Kevin. I'm very happy to be here, and thanks for the invitation. I'm going to tell a story. I'm not going to tell the whole story because there's not enough time, but there's a particular direction in which all this work went over the last 5 years that I want to emphasize. So that's what I'm going to do. So ever since I've known about computer science, which I realized was 1965 when I took my first course, there's been a big challenge, and that is that there hasn't been a standard textbook. In other fields, everybody knows there's certain standard textbooks that every college student studies to learn the field. And many of these are like the latest versions, but some versions of these almost any college student will recognize. But for computer science, there hasn't been a standard as I said, forever. That was really clear to people in my generation when we got our PhDs and we got jobs at universities. They said, go teach computer science. And we said, okay, where's the book? And there weren't any. I started thinking about this as soon as I had my first job at Brown. And I said, well, I've been studying algorithms, and I think that people need to know about algorithms. And at that time, there was very little knowledge about algorithms among the average person. It was all holed up in proprietary software or manuals or other things. But actually, the study of algorithms is an intellectually challenging body of knowledge. It's actually pervasive. You encounter good algorithms everywhere. And if you want to be doing good science and engineering, even in 1975, you had better know something about effective and efficient algorithms. And so really, to use a computer effectively, you need to understand how to understand program behavior, how to compare algorithms and predict performance. You need to know something about data abstraction and all the data structures and types that have been invented and how to apply them to modern problems. We could see that even in the 70s, even before when every university had just one computer. And so I started right away thinking about how we could have a textbook that we could use to teach algorithms to scientists, engineering programmers who needed to know them. We had one book, that was Knuth's book, but that was encyclopedic coverage and not really intended for use in teaching algorithms more broadly. So that was what I set out to do, and I'd say by now I'm going to claim that that's mission accomplished. I had the first version out in 1981, and there's been a bunch of versions and a bunch of additions in different programming languages. And it's algorithms with code. It's a study of algorithms where you actually have the code to work with to understand the performance of algorithms. The fourth edition, which is the red one I'm showing there, uses a modern programming model. It's our algorithms course is a model course in the recent ACM curriculum. We've completely revamped the book each decade in 4 editions. Over 750,000 sold, and this code is found in your cell phone and on your servers and all throughout the software infrastructure. A couple generations of programmers have been educated with these books. For people that are fans, or how such a book comes about, when I did the first book, there were no books that had code in them. And it was hard to get working code because there's only one computer. You only get one run a day. And to write a book full of code was a challenge. So really, I was happy if I had good code that compiled in that first book. And then in the second book, there were a lot of examples. It would say, this algorithm produces this output on that input. And I thought, well, if I say that, then the actual code in the book should do that. And I actually built the scripting system so that it actually did, so that if it said in the book that if you give it this input, you get this trace, it was produced by the code in the book. It was a great system. That's a different story. Then I thought it should be more scientific, and I should really, if I'm going to recommend that one implementation or one algorithm is better than another, I ought to have a scientific study that proves that. And that was a huge amount of work because I had to implement all the different competing things and get realistic scenarios and run experiments. And so that was really more than the 1990s. And then people wanted things in different programming languages. That was also a thing. But anyway, by the third edition, really meeting performance specs. And then the fourth edition, really, most people just wanted to know the best one. They didn't want to know the losers. So it's a little more streamlined and can be used, just a 1,000-page book that can be used to teach people the important algorithms that we know. So that's, I'm going to say, mission accomplished. But as the decades wore on, what I realized that I still wasn't accomplishing the main goal because a lot of students were not prepared to learn a lot of the material. There's a lot of basic computer science that is kind of taken for granted when you come to applying this kind of knowledge to important practical problems. So I had to revise my goal, and this was about the time I came to Princeton to found the department, and I thought, well, if you're going to have a department at a place like Princeton, you ought to have an intro course that can compete with the intro course in physics and economics and biology and so forth. And I think the field needs that. And that's really what was missing in the preparation of students that came into algorithms. They knew how to program in some language, but they really didn't know much computer science. And so it's computer science that is a significant body of knowledge that's intellectually challenging, that's pervasive, and that's critical to further study in all academic disciplines nowadays. That in 1992, there were not a lot of people that bought into that. Nowadays, you can kind of get people to buy into it, but there's still plenty of people who won't really. And the other thing was that I knew that anyone can learn this stuff, learn the importance of modern programming models all the way up through data abstraction. The importance of the scientific method in understanding how programs behave, the algorithms and data structures that are critical to our computational infrastructure, all about abstract machines and how they connect to real ones and the historical context, and computation in a broad variety of applications, and generally preparing for a lifetime of engaging with computation. Don't want people to think these are black boxes they don't understand. We want them to think of a computer as something that they can use effectively, whatever they do. But still, there's no standard text that can stand alongside the intro text in other disciplines. So that was the 1992 goal. Now, I'll omit all the challenges that came up in trying to achieve that goal. Changing a programming language when you're teaching an intro course is a hard thing, and I had to do that. I started in C and now wound up in Java. And resources were terrible. The expense of teaching a huge number of students and having them write large programs is just never enough resources. All kinds of challenges, but this is 20th century type challenges. So what I think now is that maybe mission accomplished on this, and that's the book that Kevin just showed. So our book has 25 years worth of development. It's the fundamental concepts and ideas in the field for first-year students. We teach programming in Java all the way through data abstraction and theory of computation, all the way from Turing machines or regular expressions all the way to intractability. We have machine architecture and circuit design all the way from gates to machine language. People learn the historical context. I like to say that nowadays, every college student knows who Einstein was. I think every college student should know who Turing and Shannon and von Neumann and Boole are. And our book, I think, I'm not ashamed to put it up with the standard book in other disciplines. And it's now the basis for Princeton's most popular course. Nearly 2/3 of all Princeton students take this course. And it's also a model course in the ACM IEEE curriculum. So it's an interdisciplinary approach. The way we succeeded to get so many students was to embrace what's going on in computation in other disciplines and to leverage their knowledge in those disciplines. It's not a course about a particular programming language or about a particular skill. It's a course about computer science and its impact. And just as an example, what we do is we put everything in the context of applications. So this code here is Java code that uses a simple graphics library to produce a simulation of a bouncing ball. So that's a fun thing that students can do sort of on day one. But that same code, if you give it object orientation, then you can have lots of bouncing balls. But actually, to make this one happen, you need to know about priority queues. So this is out of the algorithms simulation. Or if you use a little F equals MA, you can do an n-body simulation. And our students do this as their third or fourth programming assignment. That's our example of a nested loop. To do the two, everything interacting with every other. And at the same time, we can make the point that computation is essential. We don't know the math to describe these curves. The only way that you can understand this is to do a simulation of this sort. 20th century is about math models. 21st century is about computational models. Anything you want to do, you better understand computational models. In their third or fourth, and this is all data-driven. So you can make any kind of planetary system you want, and we've seen thousands of planetary systems with all kinds of crazy interacting 8-way orbits that the students have come up with to engage them with computation while at the same time teaching them a basic concept and the importance of computation in physical world. Oh yeah, got it out of there just in time. Wasn't a perfect simulation. So by 2011, this stuff was mostly done. The book wasn't complete yet, and I'll get to that in a second. We're writing the computer architecture part, which is a complete design of a computer from the switch up, was a really time-consuming exercise. But it was mostly finished in 2011, and we had huge, it seemed like huge enrollments. Maybe double what we had in the bubble around 2000, and quite a few Princeton students. And we had lots of enrollments in algorithms as well. And so this is just the prologue, because in 2011, so that was about the age that my father retired to Florida and started playing golf and shuffleboard. And I'm thinking, this looks good. We're in pretty good shape here. I just have to finish that one book. And so now what I want to talk about is what happened next. So there were a lot of disruptive changes that we're all familiar with, and I want to just highlight a few. So the first one has to do with libraries. I picked up a copy of the New Yorker. This is over 10 years ago now. And there was an article by my colleague, Anthony Grafton, who's a historian, who loved the New York Public Library and was talking about the various plans they had and changes to the library. And he was arguing that you got that narrow path between the lions up the stairs, and it leads, as it must, to crowded public rooms where the sunlight gleams on varnished tables, and knowledge is embodied in millions of dusty, crumbling, smelly, irreplaceable documents and books. Now, I don't usually do this, but I just walked right over to my computer and wrote a letter to the editor. And they published it like the next week, or not that long. And so here was my response that I just didn't have to think that much about. And I'd say it's fine that we might have to worry about old books, but there's really a lot going on that doesn't have anything to do with old books. And really what we need to be thinking about is this question. What's the most effective way to produce and disseminate knowledge with today's technology? How can we best structure what we know and learn so that students, researchers, and scholars of the future can best understand what we're doing today? I think that's a much more important and more difficult question to address than whether we can put the contents of libraries on the webs or whether we should. And we still don't have good answers to this question. In the 20th century, even say at this institution, say 20 years ago, students would spend a lot of time in the library with books. Faculty members would have to go to the library to get copies of journals for research. The library was a central part of the activity. But nowadays, students, well, maybe they go to the library because they have comfortable chairs and good woodwork, but nobody in the faculty goes to the library at all for research. But we're still investing pretty much the same. I don't do that at Princeton. But I think, you know, in the 2020s, which are coming up pretty soon, we might have a few book museums, but really everybody else is going to have some kind of digital library infrastructure. But how are we going to create the content for that? Are we really going to be submitting Word files? I'm not quite clear how knowledge is going to be disseminated in the future, and are universities going to play a role? Is there some activity in figuring out what this is going to look like? Just to have one example I just saw last week, this is a new library in China. You know, it's categorized as a book lover's dream, this incredible except those aren't books. They're just pictures of books. So that's where we are. Okay, so that's a disruptive change. I don't know where they put the real books. The architect said it wasn't the point to store books. I don't know exactly what the point is, but okay, so that's one, libraries. Second one is textbooks. If you pay attention to what's going on with textbooks, you can see it's kind of a road to ruin. The prices have gone up so high that students are forced to rent. They don't own books anymore. If you teach an upper level, say I teach an upper level course in analytic combinatorics, and I say, take out the text for that complex analysis course you took last year. And they say, don't have it, don't have access to it, because I just rented it. I think it's a road to ruin. Princeton U Store used to be a magnet. Our friend Philippe Flageolet used to travel to Princeton in order to go to the bookstore to see the math books that are available. Now if you go to the website, there's not even books on the website. So again, what's going to happen with textbooks? Is there room for a good textbook, or is everybody just going to get all their information for free on the web? I'll have something to say about that later, but already this change has happened and the students don't own books and nobody really thought about it. And I think it's a bad thing. And then this one. So remember 2011, I thought I was done. Really, January 2012, I got called to a small meeting in Nassau Hall, this administration building at Princeton. Well, okay, our administrators don't look quite like that, except for the no sign, maybe. So a small meeting, there's this thing happening. Do you want to teach online? And people had asked me about that before, and I always said no. It's way too much work. It's going to cost way too much to do it properly. People are going to have big expectations about the quality of this thing, and you're not going to give me the resources I need to create it, I don't think. So I just said no. But then 2 months later, I get a call saying, well, our trustees have decided that we should do this and we're going to do it anyway, so are you in or not? Yeah, we have to know by tomorrow. And so I said, well, I don't want somebody else doing the first online course on algorithms, so I have no choice. So, okay, we'll do it. And this is the Coursera. This is how Coursera got off the ground, was going to university administrators and convincing them of the promise of online courses. And they did a good job in setting up a platform that preserved the course abstraction that lots of people could take advantage of. And many of you kind of know the story. And what we realized immediately after saying yes, it was like, okay, what are we going to do now? This is Kevin Wayne, my colleague, and I, that really what we're doing is pretty well suited to go online. And actually, we got it to happen pretty quickly. By the summer of 2012, we had our first MOOC out. Then one thing led to another. Well, there were plenty of challenges in getting further. We had a lot of things to think about in terms of the presentation style and the software. Who owns it? There were lawyers involved, so my wife says I can't make this talk negative, so I have to skip by these slides. So here's a summary of our MOOC experience. So we produced 6 courses. They're like Princeton courses split in 2. 4 of them are already deployed on Coursera. Actually, 6 are already deployed. There's about 70 lectures, and each one of them are 60 to 90 minutes. There's 3,000 lecture slides, and I'll have something to talk about them later. And we've reached over 1 million people with the courses. The distribution model is still kind of not there, but the MOOCs are happening. The algorithms continues every year to draw 200,000 enrolls a year. The advanced courses are now freely available. You can just Google search for analytic combinatorics and you can take a course on it. We have an associated textbook for each one, and I'll be talking more about this a little bit later, with the lecture videos and also associated web content. I have a whole talk that describes kind of the details of the MOOC thing, but like I said, I want to take it in a slightly different direction now. And that was to think about actually exactly how are we going to be teaching computer science at Princeton in the future. And I remember very clearly the moment when I finished the final lecture in computer science, which was a simulation of this processor with very detailed, really micro-programming of what's going on. Really terrific, but a huge amount of preparation. And the last slide had 40 builds on it. That means 40 clicks as stuff happens. And I go into the process of creating these things, but once it's created, it's like rehearsal. And a lot of preparation go in. And there were a lot of retakes in that one, because I wouldn't always have the right words to go with the right clicks. And when I finished that, I said, I'm so glad that one's in the can, because I'm never going to be able to deliver that lecture again. And then I thought for a second and said, well, wait a minute. If I can't deliver the lecture again, like what's going to happen when I teach the course in the fall? And if I can't deliver the lecture again, how's anyone else going to deliver that lecture? So it was like immediate to me, we got to use the studio-produced lectures. They're there. They're great. There was a lot of preparation. We have to use them. I don't know anything. I haven't thought it through really much. And everyone else said, but it's our biggest and best course, and you want to change it? And that's like a major change to use those lectures. And again, I have to leave out a lot of the argument, the 6 months of my life of how is this going to happen, what are we going to do, are they responding to all the questions that come up. But for me, it wasn't really do this or do that. It was like there was no question. This was the only way to do it. There was no question in my mind. So what I decided was I'll do the first lecture, and then I'll tell them at the end of the first lecture, that's the last lecture. All the rest of them are going to watch online. This was typical. You've all had the first day of class in September. First of all, it was hot, really hot. I had a student one time tell me, if you see the professor sweat, that's when you learn the best. I was like soaked, you know, because it was so hot. The lecture hall was too small. More people wanted the course than would fit in there. So they had to televise the thing in another room anyway. And it's such a wide thing that half the students couldn't even see the screen, and then the sound system blitzed out halfway through. So we've all been through that, right? So what happens to the poor students in the old world? Well, out of luck, but no problem convincing them to move online. No problem at all. So that's what we did. And then after half the semester, we asked them, what do you think of the online lectures? 82%. I had no idea what we were going to get. I wouldn't have cared if they had said 20%. I would have said, OK, we have to improve things. But the students absolutely loved the active participation in consuming the online content. And these are some comments which are really funny from that first time for us. Prepares me for a lifetime of active learning online. And I have to tell that poor student there might be other courses that doesn't get that. I like the system. It really lets me go at my own pace and rewatch if I need to. And that's the key. That's why the online lectures are better for students than live lectures, because they can go at their own pace. A lot of them go play them a double or triple time, or they can stop and rewind. Video lectures are amazing. I believe many of classes would benefit from this. And again, I wasn't fishing for these kinds of comments. This I knew was the only way to do it. And it was also beneficial for the course staff. For one thing, office hours pretty much ended. Students didn't have any questions. Usually, in the traditional thing, the student gets lost after 5 minutes of the lecture. They're writing down notes, not paying attention at all. They come to office hours to get you to explain their notes on your lecture. But with this, if they don't understand it, they just stop it and replay it till they do understand it. No office hours. Why would I walk across campus to ask this question when I can figure out the answer myself just by replaying the thing? There's a lot more time for interaction with students in small groups because you're not worried about getting the basic material covered. We also instituted different mechanisms for interacting with the students. I'll talk with that a little bit. But it's all about interacting with students, not preparing and delivering lectures that are better done in the can. And another big one is scheduling complaints. Student misses a lecture because the sports team is in a national championship, or there's a religious sports team's in a national championship. Fine, you can't come at 11 o'clock on Thursday. Fine, watch the lectures. I have to worship my particular whatever on Friday mornings. Fine, watch the lectures Thursday night. Whenever there's no scheduling chances, nobody's got an excuse to not watch a lecture, and that was really a huge positive effect for the course staff. That spurred our enrollments really a lot. And so now this is, I haven't updated these figures recently. We're up to 2/3 of all Princeton students. And the biggest course at Princeton, and actually it makes sense because we're bigger than the biggest room, both semesters, so we got to be the biggest. And even algorithms, which is so this is a full year of computer science, we're up to nearly half of all Princeton students take algorithms. Not all engineers, all Princeton students. That includes the sociologists and the medievalists and the chemists and the physicists and the math, and plus all the engineers. So what I want to talk about a little more today is how these two experiences, the MOOCs and scaling at Princeton, are going to help us address the next challenge of trying to get other colleges to achieve these kinds of percentages. And one bonus that's really important is the combination of the scalability and the idea that we're teaching one course for everyone really promotes diversity. Where many institutions wind up, and we were there at Princeton, is there's a different CS course for every discipline, for political reasons or maybe pedagogical reasons. But the problem with that is that only one of those courses or a few prepare students for the next course. So it immediately cuts out a lot of students out of the experience. Whereas if everybody's going into a single course, everybody's well prepared for the next course, and this shows up in the numbers. We have a lot of students that we never would have gotten into CS at all come in to the big course, because it's a good course about computer science, not a boring course just teaching a programming language. And then a lot of those go on to become majors. So we're also the biggest major at Princeton. I know a lot of these are demographic trends too, but still, in particular, women and minorities come into the big course. They're the same as everyone. We provide what they need to be successful, and they can replay the lectures if they need to or learn in their own way, flexible with what they need to get through. And we have nearly 40% women majors, which is more than twice the national average. And that's without even trying to address that problem. As you all know, most computer scientists are completely overwhelmed with huge numbers of students, and we don't have time to address these important social problems. We're just trying to get through the day. But anyway, the broad approach, I think had a desired outcome. But this points out a problem in that nobody could sustain growth at this scale. We created a problem with our success. So if you look at the number of majors or number of enrolls per semester or whatever, at Princeton, computer science is 10% of the university. But we're only 5% of the faculty. Well, how's that supposed to work? So 3 solutions that I can think of. You could double the size of the faculty. Well, a lot of places are trying to do that, definitely increase the size of the faculty, but that doesn't help me like next semester or the semester after. Still working twice as hard as everyone else. You double our salaries, that'd be nice. But that's not enough because we can all earn 10 times what we're earning in industry, so that's not going to work. I could limit enrollments, well, that's crazy. So it's definitely a bump in the road. But I think what it says is that if we're going to continue to succeed, we need a new model. It can't go on the way it is, as Kevin just pointed out. Can't go on the way it is. And the good news about that is not only are we computer scientists, so we know how to embrace technology, but also if we can just do our job here, it's not that much more work to reach huge numbers of people outside of here. And that's enough to motivate people to do these things, and I'll explain. So I want to remind everyone, purpose of the university is to produce and disseminate knowledge. And I don't know who first articulated this. A lot of us in recent decades are kind of stuck on the produce part and maybe taking the disseminate part kind of for granted, but it's definitely an important part of it. And so at many institutions, really it's a research faculty. Excellence in teaching is important. People don't come to universities unless they want to be interact with students and be excellent. But they have to be devoted to research. You have to do both. This talk, what I want to say is, if you just replace your live lectures with online videos, either make them yourself or use somebody else's, and you embrace technology and think about what you're going to do, and everything that you do it in a manner that scales. Oops, sorry, I went the wrong way. Then you can focus on the student experience. And it's more efficient, it's better for the students, and gives you more time for research while still giving an excellent student experience. And I'll explain in more detail. So the old model, which was a standard and still used widely in this country anyway, is there's standard textbooks. And so authors and publishers make a big investment, and some get widely used. And the distribution model is the publishers sell the books to students, the teachers adopt them, students buy textbooks. Teachers prepare to deliver lectures to introduce and inspire the material and inspire the students. Sometimes the author prepare the slides for the teacher to use. I've done that plenty of times. And then it's the teacher's job to assess, grade, and certify that the students know this stuff. That's the old model. And there's a lot of pain points in this model. So one of them is that you got lots of people delivering the same lecture. That's inefficient. As I mentioned, there's a problem with textbook publishing imploding and not clear that that distribution model is going to survive. The passive lecture experience is unsustainable. You're not going to be able to keep students happy by delivering lectures in large lecture halls. And people around the country are already seeing this. Most are not willing to admit. MIT, for example, admits that attendance at their lectures are less than 20%. If you got less than 20% coming, maybe you should look at a different model. The other thing is, although more and more people are embracing technology, that's definitely another pain point with the old model, and I'll talk about that. So our new model is to integrate kind of the abstractions of the old model, but to embrace technology to make it more efficient and effective. So we're going to have a textbook. I think textbooks are important, and I'll explain that. We're going to have video lectures for introduce content, inspire students to study it more. We have web content, extensive web content for students to interact with the material while they're using their computer. And we're also going to have web services, and people, this is not just us, people widely are realizing that assessment and even certification could be done with web services. So the benefit of this is it's consistent. Everybody gets more or less the same experience. It's scalable in that if you can do it for 1,000, you can do it for 10,000 or 1,000,000. And it's flexible. And it's active teaching and learning, both on the parts of the students and the teacher. So let's talk about the abstractions one at a time. So I think textbooks are here to stay. Now, I'm going to say that because I have a lot of them, but it's well understood since the Greeks. Gutenberg enabled it for the masses. It's still in widespread use. There's still lots of college students using textbooks. A textbook articulates what students can learn about a subject in a semester. That's the abstraction part of it. It also distills a lifetime of a professor's experience to be passed on to future generations. That's what the textbook as an abstraction does. And it provides a reference point for people studying later on in the curriculum. Everybody knows what's in the textbook. That's what the students are supposed to know. If they don't know it, they can go back to the textbook. That's what the textbook does for us. Now, the problem is that books are difficult to write in this textbook publishing industry imploding, but still, I think the textbook's here to stay, and I'll talk about it more in a minute. Okay, the lecture. On the other hand, the lecture, it's been around for a long time. You're an instructor, you very much control yourself, the pace and direction of the thing, and you can interact with students and adjust. And getting together with students on a regular basis is really an important part of education. And definitely there are great teachers that can be effective at inspiring large groups of students. That's all good. The disadvantages are that there's a lot of time and effort to prepare a good lecture. There's a lot of duplication of effort. That's unnecessary. But the main problem is it places students in a passive role. And there's a lot of research on this. I can provide references a yard long, that the problem is that when you set it up that way, you're saying to the student, you sit there, I'll teach, you'll learn. You don't have to do anything. And that's basically the opposite of what you want to do when a student's trying to learn. The other thing is, as our ability to communicate effectively is enhanced by technology, instructors have to know and do more in order to compete. Oops, sorry, I'm going backwards. Oh, wait a minute, I gotta, oh no, sorry, I got the wrong. So this is a famous quote that's attributed to lots of different people. Lecturing is that process by means of which the contents of the notebook of the professor are transferred to the notebook of the student without passing through the mind of either. So the question is there a practical alternative to the lecture? And of course, I think there is. And I'll talk a little bit out of it. So one good news is that lecture presentation materials are evolving to a really amazing standard of excellence. So we used to do Chalk Talk, and there's people that still cling to Chalk Talk. There's this one, I'm embarrassed to even show this, but like I taught this way for a long time, where we'd write stuff on pieces of plastic and they would put it on this thing and students couldn't see who you were, and it's so much work to do it, and terrible, terrible way to communicate. But then along came PowerPoint. And that's the way most PowerPoint presentations were. So I submit that PowerPoint was not a good thing, and a lot of people, I think, would agree with me on that. However, things continue to evolve, and now you can develop really effective presentations now, state of the art, an individual can. This is from my analytic combinatorics class, and yeah, it looks like there's way too much on that slide, but what we do is we present it a build at a time. And that is a very effective way of presenting. So this is like people said, you have to do math with a chalk talk. You can't do it this way. They say, no, I think I like this way, where each line of the derivation I can explain. And I can say, that's true because of this theorem. Remember that theorem? And I can just put it there and then get through the derivation. It's controlling the pace through builds is a really important thing, and including all the details. And when I've finished making that slide, for one thing, there's decent chance there isn't an error on it, at least after I've used it a few times. Chalk talk, no chance there's not an error. And the student wrote it down and didn't understand it, and they come into office hours. It's totally inefficient, totally inefficient. And then I can do much more detailed things like plots, like the gamma function is really important to this material, so that's the gamma function. I also can include a story. I learned about telling a story in a lecture when I did the MOOCs, which I wish I had learned earlier. And then a lot of times drawings and things like that can be done. Now, sure, I could draw this stuff on the board, but that would be like drawing this one thing would be the one lecture, and there would be errors on it. But in the online presentation, I can show this thing and talk about it for maybe 10 seconds and make a really important point. And if a student has a question about why is that one there, not that, they can see it right there. It's all about the quality of the presentation. The other thing is, it's not that big a deal to do, what every local TV news show does or whatever else, and apply some professional standards to creating the part of the lecture that includes me. Really not that big a deal. Most of the effort is preparing those presentation materials, but the actual number of, so it'd be like 2 hours in the studio for a 1-hour lecture, and then some editing afterwards. But by far the most time-consuming element is what's going to be in the lecture, and let's make the slides that make that point. And that's, I think, the way that it should be. And the thing about it is, once it's created in this way, it's consistent. Everybody gets the same experience. But the main thing is that the online lectures transfer it from passive to active. Students are actively learning at their own pace. They don't click on the thing unless they're going to watch it. And they know they have to click at the thing. That's why they're at the university. Typically, beginners use a slow pace at first, but advanced students will do double or even triple speed. Lots of students watch at triple speed. And so what I say to students or anyone taking a look at my lectures is increase the speed until you're not bored anymore. And then you're fine. And then if you get confused, slow it down a little bit. And people find their speed. And the technology is amazing for efficiently reducing that student experience from getting up, having breakfast, getting in a particular chair at a particular time, staying awake, listening to the thing, to, okay, I got 20 minutes, I can do that lecture. And maybe I'm in the team bus. I'll get to that. So everyone's pace varies throughout the course, depending on the circumstance. They actively choose the time and place they learn. That's active learning. Some of them do it in the library. Some of them do it first thing in the morning in the library. Okay, so there we go. On the team bus, that's fine. And this one, younger people. This one got a lot of likes. You wouldn't believe it, but it did. They're always available for, if you didn't get that, ask somebody young to explain. So no office hours, promotes diversity, and exam review. The lectures are there for exam review. So all of these things are positive things about online studio-produced lectures. Okay, web content is another part of what we do. People don't go to the library for content anymore, they go to the web. I don't have to sell that really much anymore. There's no physical constraints, available to everyone, should be always up to date. And the main thing for us is it's got content types that are not available in print. Things that you can't do in a book. And I'll give an example of that in a minute. When should I go? Till 20 of? Or? Yeah, sure. Okay. The other thing is not just content, but services. So people nowadays use tools for creating. There's online forums, there's testing and assessment tools, and there's video delivery platforms. All of these things are essential in education, and people must use them. So in the 20th century, the university would buy a huge, all-encompassing learning management system. I think people are moving away from that now and just either coding it up themselves or finding out what friends are using and what's good and using that. So you have things that solve one problem and solve it well and that interact in a reasonable way with each other. That's what's emerging. And that allows a lot of progress because a new one can come along and be better. So I want to give a case in point, and that's Algorithms 4th edition. So we've got a textbook, we've got lectures, we've got the web content and services, and this model we use at Princeton. Other institutions are beginning to use it, and various pieces of it reach large numbers of people. So the book, I already talked about the book. That's a repeat of the same slide. The web content, so this we call a book site. If you type in algorithms, we should still appear on the first page. So this has, it's tied tightly to the text. It's got synopsis of the text, not the whole text. We tell students it's for use while they're on the web. And so let's see, where are they? So it's a web presence, so if you search, you can find stuff. And nowadays, when I write code, I just search for that name of that thing, and it comes right up on the Google window. It's got real code that you can just download and use. It's a living document that is for use while coding and exploring. There's, for algorithms, there's tens of thousands of files. There's 1,000 Java programs that people just download and use. 6 million page views last year, 1 million unique users last year for algorithms, web content. It's a big part of how students can interact with our content. There's much more on there than is in the book, and so that's also a resource for people teaching with the book. So there's the lecture videos. Those are available on Coursera, so you can just go to Coursera and take the Coursera course, or you can buy them at a reasonable price from Pearson, and we're trying to get Amazon instant video too, and that'll come soon. And these are widely used around the world and already have reached 1 million people, the videos, in all kinds of different contexts. In Ukraine, somebody rented an auditorium and played the videos, or other people just download pirated versions on YouTube. So anyway, they're widely used. And web services, I'll just quickly go through this. So we have a program assessment infrastructure that allows us to provide individual comments on student programs that we use for lots of courses at Princeton. We also do automated program testing, and I'll just talk a little bit about that. It's very fine-grained. It does sophisticated performance tests, and it's packaged so that other people can use it, at least for the program examples that we assign. And then also quizzes and exams can be done on the web automatically as part of the web services associated with algorithm. And I'll give a couple of examples of that. It's just enough time, I think. So quizzes and exams is interesting. So I've always wanted this, and now I have it. So the first example is combinatorial questions. So this is out of computer science. So this is like 50 facts about computability and intractability. So I just write the 50 facts, and it's like true, false things. But then I can take those 50 facts and generate questions, true, false questions for exams, or for student self-assessment. And say, just pick 5, and they have to fill in true, false, or nobody knows. That's 2 million questions. So just writing those 50 things once, now I've got a tool for students to drill and for instructors to use to give exams. And we have hundreds of questions like this. It's preparing ahead of time to make the grading part scalable. Here's another one. We tell the students at the beginning of the algorithms course, you're going to have to answer a question like this with different data. This is strings, and at the left there it's input. At the right they're in sorted order, and in the middle is intermediate stages of various sorting algorithms. So you can't solve this, and the easiest way to solve this is to understand what the algorithms are doing, and the students know they have to do that, and they can drill using different data that make sure that they understand the algorithms. And this one is like really a lot of questions because you can put in any data at all. But you get the idea, and as I said, we have hundreds of questions like this. This is called Coursera, and there's a demo website on there. You see how it works. For some of them, we can, if they type in the wrong answer, we can tell them you made a mistake and you should go back and read this, or you made a mistake because you had this backwards, so try again. So we can provide feedback that helps them improve. That's with nobody intervening. Students use this really a lot. That's how they prepare for exams. So what it means, oh yeah, there's the demo. Demo Coursera.io, and you can see a little bit of it. So we can do quizzes and exams automatically. Don't have to grade those anymore. Used to be that was what people spent a lot of time, was grading that stuff. That's, and that scales really well. I'm going to have a tab on the website that's available to everyone that brings people to quizzes. So again, the technology really dramatically improves the quality, consistency of assessments, not to mention the efficiency of poor people who are teaching overloaded classes who now maybe don't have to grade. And I don't want to spend too much time on program assessment just because what we're doing is not unique there. People are using lots of different things. I think what's unique about our program assessments is that we do very sophisticated testing, including probabilistic tests. It's not just here's the input, here's the output, check. It's how much memory did you use, and does your algorithm behave properly according to statistical tests on randomized inputs. So again, lots of applications, and again, dramatically improving the quality and consistency of the assessments. That's web services. Sometimes I think we worry too much about grades. We've all encountered students like this. I was up all night grading those professors and all those papers, and all you care about is whether they're going to be in alphabetical order. Another factor that we're finding very effective with scaling is bootstrapping. So we have lots of students. We can take the students who have done well and use them to help grade the course below. And we can apply technology so there's no conflict of interest type thing. So even for a huge, well, not huge by your standards, but by anyone else's standards, like a class of 500, we can get all the programs graded in an afternoon with like 50 undergraduates. Applying technology in a reasonable way and providing feedback to each individual student. And the other thing is software development. This has amazed me in recent years. Every student wants to create Facebook. And so what do they know about? Well, some of and they have to do research projects, and they don't know too much. One thing they know about is how they can make the world around them better. So like Princeton's course registration system was written by a student. All the students, they just scrape the registrar site. All the students use their thing, which works on iPhone and Android and everything, and then they put it back on the registrar site, and done by a student. And the registrar tried to stop it by changing their site. Nobody registered for anything. And it went on for a day. There was panic up in the registrar's office. But then the students wrote a meta tool so that if the registrar changed the site in any way, they could quickly, in that language, change their screen scraping thing, and it was all fixed and for all time. That's what we get out of students. You don't get that any other way. They understand the shortcomings. We just put them to work, and we get much better software than we can get any other way. Much better software. All the stuff I've described is created by students with semester projects, senior research, or summer projects. Okay, I'm just about done. We also have this for computer science now, though all the web services are not quite there yet, but quite a bit of it is. And for analytic combinatorics and analysis of algorithms, and those things are freely available. That's not a MOOC. You can just search and you can teach a course based on these, and lots of people are doing it. As you can tell, we're experimenting with different distribution models and trying to find the right thing, but we are reaching lots of people. Analytic combinatorics is a course that maybe I could get 8 or 10 Princeton students to sign up for. Last year, I think something like 30,000 people took it. Pretty good. Not much more work. Okay, so, oh yeah, I got to do this one. I think I've already covered all of this stuff, pretty much. And I'm out of time anyway. So the whole idea is, with this model, teachers have time to help students succeed. And it's not that difficult to expand to reach lots of people around the world. And don't forget, the purpose of the university is to produce and disseminate knowledge, and we can do this disseminate part really to millions of people without that much extra work. Just one last paradox, and then I have a postscript. One thing says, what about interaction between faculty and students? The paradox is that it actually increases and enhances personal interaction. First thing is, the videos are way more personal than one might think. Every one of those students spends like hours watching me like that's far from them. They all think they know me. I walk across the Princeton campus, or I go to a conference in San Jose. People know me. They walk up to me and open the door and whatever. I get waves, smiles, selfies. Don't forget Sedgewick and Chill. And this was just posted yesterday. It says, dress for the job you want, not the job you had. Steal his look. So that's, you know, so memes, you know, it's nuts. Now, the thing is, the quality of interaction is way better than with live lectures. Nobody's taking notes. The interactions are about the ideas, about connecting things and applying ideas. It's not about what was the bug in the lecture. Teachers can also explore, teach their own slant on things without worrying about covering the basics. Our teachers love that aspect of it. I love this quote. This is David August, who taught the course, is teaching the course that is using my lectures right now. We focus on outcomes. We care about student experiences. If we were to try to do more or try to enlarge groups, the experience would suffer. It's about student experience. And with technology and online lectures, we can improve it dramatically. So that's what I think about the 20th century, and that's what I think about the 21st century. Okay, so now mission accomplished. I hope so. And let me just finish to make the question and answer part more efficient. I'll give you a lot of questions that I've heard. So isn't it difficult and time consuming to do this? Yes. 50 to 100 hours preparation per hour of lecture is what I spent on it. And not only that, I had to know how to use a lot of stuff, and I don't even remember half the stuff. And the new version would come and break everything. Terrible, terrible interaction with technology. But easier than writing a book, and particularly after writing a book. So it's like, I don't know, 1/5 the effort of writing a book. And the other thing is, not everyone needs to do this for their lectures. You can use somebody else's and then have more time for research. The focus is on the student experience. In the 20th century, you use a textbook. 21st century, use a textbook and online lectures. And students are way better off. Oops, sorry, I went the wrong way again. Okay, I think my administration will fire me and use your lectures. Well, I worry about that myself. Like, they're using my lectures, but I'm not getting credit for that, like right now. But I really don't think that anybody's going to talk about cutting costs by firing teachers. And actually, in CS, I think there's an argument to say that already our successors have been fired because we don't have enough faculty. But really, it's the teachers are needed for this to help the students succeed, certify that they did so, not prepare and deliver lectures that everybody else is preparing and delivering. Doesn't make sense for hundreds of professors around the world to be preparing and delivering the same lectures. They're not going to spend the prep time. And by the way, if you're teaching an algorithms course, I've had many students tell me they get bored in that course and they just turn on my lectures and send me an email saying, I'm sitting in a boring class watching your lecture, thanks for doing it. Okay, administrators, why aren't more faculty developing online courses? Well, it's a lot of work, and anyway, they get promoted on the basis of their research, not on the quality of their online lectures generally. Have you done a scientific study? No, you're not even going to give me the resources I need to teach, but how about if you provide me officially the percentage of students that are attending traditional lectures? Oh, we can't do that. That would violate privacy concerns. Harvard got in a lot of trouble for trying to do this not that long ago. But I can tell you every section of every lecture, you know, who watched it and for how long. I don't do that. A lot of people that I work with want to do that, but I feel that that's violating privacy. I don't care if a student has to watch it 100 times or 2 times, and I don't care if I could be more effective knowing that. I think they deserve to do whatever they want with it. As long as they do well on the exams, I'm fine. And by the way, as I said, nobody did a study to show that it was a good thing to do PowerPoints, obviously. Okay, what can we do to improve things? Embrace technology, develop teaching professors, and we need a large number of them who can deal with the blended classes and who can help students succeed. Give some support and real incentives for people who want to put time and effort into teaching. We should be doing research on this stuff. There's all kinds of innovation possible. We can't leave it to industry. We should do it at universities. When you do this, you have the opportunity to attract the best and brightest to the university that way. Used to be you had to build a big library and fill it with unique books. That's not going to work anymore. Another way is to be a center for online learning. And you really want to develop academic leadership in these sorts of fields. So how much is it going to cost? I have no idea how much it's going to cost, but it's way less than other things that you're spending on. And really, you should be thinking about investing in it at the scale that you're investing in the library. The library is not impacting what you do. You're spending a lot of money on it. How about spending some of that money on this that does impact what you do? Really, you can't afford not to embrace it. Okay, so just the final thought. This is John Hennessy, at the time was president of Stanford, in the New Yorker. Universities, like newspapers and music companies and much of traditional media a little more than a decade ago, are sailing in seemingly placid waters. But there's a tsunami coming. He's taken a lot of heat for that, and our own president, Shirley Tillman, 2013, says, well, what happened to that tsunami? I think we have to do some hard-nosed thinking. These people, the university administrators around the country, listened to the Coursera startup line thinking that they were going to make a huge amount of money within a year because people were going to buy their content, which I don't even know how they thought, where they thought they were going to get it from. And when that didn't happen, they said, well, That doesn't make any sense. And I think that they just had some bad business models and they ignored the cost and opportunity for content creation. I think there's going to be 21st century models that connect content creators and consumers that will cause the tsunami. But for me, it looks like a tsunami. I have a lot of online content. I have a lot of lecture videos. I'm reaching millions of individuals all by myself with no support from anyone. I was lucky in the 1990s. I had my 4 kids all as students at Princeton. But I think I'm going to be teaching my grandchildren now. Thank you. That's all I have.
Okay, we have time for maybe a couple of questions. Yeah, Karen?
Can you break down those 50 to 100 hours per lecture? What was that all about?
Well, those slides are really detailed. So there's a lot of just creating the drawings, creating the content, interacting with all the different tools, making the builds, editing, and refining. So I'd usually do like 5 passes over it. And then I have worked with Kevin. I'd have editing passes he would respond to. But those combinatorial drawings and those plots, they take a long time to do right. And to get the math edited and that's...
Another question up here?
Yeah, that was a very good presentation, and if the autonomous vehicle people were as positive and convincing, I appreciate them a lot more than I appreciate what you're doing. One thing I'm wondering though is, towards the end you had a question, what will it cost the institutions? And I was thinking the cost to them will be 0. Because if I was running an institution and I wanted to teach your 4 courses, I'd use your material.